Hello, welcome to the lecture series of Perfect Academy. Myself Ishwar, I'm working as a physics faculty here. So this class I'll be giving a lecture on one of the important branches of physics called modern physics. I'll be presenting you this topic in this class, in this lecture. So the important topics that we are going to learn, I'll mention in brief. First we'll be studying about photoelectric effect. Then matter waves. And then comes atomic and nuclear physics. So these are the key topics under this heading. We're going to discuss one by one in the coming lectures. So first of all, before going into these topics, let us have an understanding of what this physics is all about. What is this physics, modern physics? What is this all about? We all have studied so far about different branches of physics like mechanics, electricity, magnetism, thermodynamics, optics, and etc. etc. And we know how to deal with these concepts. Suppose if I give two masses, I can easily find out the forces exerted by those two masses between or on each other using the gravitational laws, Newton's gravitational laws. And then if I want to find the acceleration between them, given some initial conditions, I can find out the acceleration, velocity, time, whichever is required using the kinematics and equations of motion, Newton's laws of motion. Similarly, we have studied in optics the diffraction, polarization, interference patterns, and we use the concepts of wave theory of light there in order to explain the phenomenon of diffraction, polarization, etc. But these are all the macroscopic objects. Like we all are in the macroscopic world. We can see these objects, we understand the physics behind them, we can feel them. All these things are visible to us, or in a sense we can view all the laws, or we can view the objects, their behavior, or how they are going to behave in the future. But the same thing, the same laws, are they valid when we go into the microscopic world? When I say microscopic world, the world of subatomic particles, just like electrons, protons, neutrons, all that in an atom. Can you use all the same laws what we have studied, like Newton's laws of motion or wave theory of light? Can you use all those things? The answer is no. We can use them to some extent, but the phenomena that we see in that microscopically can't be explained only using the classical laws of physics. Classical laws means you can say it's Newtonian laws, what we have studied so far. We need some more theories to explain and to understand the phenomena that is being seen in the microscopic world. And those theories were developed in the very recent years, like just in the beginning of 21st century, some 100 years before. That's why the name given is modern physics. These theories were recently developed. They are just some 100 and 120 years old, that's it. Now what these theories, why do we require these theories? As I said, the classical laws are not sufficient. For example, I will take an example. We know that atoms contain nuclei, and nucleus have the nucleons, they are called protons and neutrons in it, and electrons, they revolve around the nucleus. Yes, they revolve around the nucleus. We know this. They are orbiting around the nucleus. This is the model proposed by the Rutherford. But then, when we accept this model, We know that electrons are continuously revolving around the nucleus. Something has to strike our mind. What is that? We said that electrons are continuously in motion forever around the nucleus. But classical laws tell us that some object or any particle, if it is in continuously motion, it will lose energy after some time. It will continuously lose its energy. Similarly, a charged particle, electron, if it is revolving around the nucleus, they are in circular motion. All the electrons are in circular motion, and we know that they are accelerated. When they are in uniform circular motion or in circular motion, we say that those particles are being accelerated. So when a charged particle is accelerated, it continuously emits electromagnetic radiations. So electrons should emit radiations, should lose energy continuously, and finally it has to take, suppose this is the nucleus and this is the original orbit of the electron. Once it loses energy, it has to take the spiral path like this and finally will fall into the nucleus. What will happen when electron falls into the nucleus? The atoms will collapse. But do you see this thing is happening in the physical world? We see all the atoms, we see the matter everywhere. All the atoms are stable here. Every atom is stable. We don't see this picture. But if you use the classical knowledge, the electron has to lose energy and finally fall into the nucleus. But that is not happening here. So classical laws cannot explain this concept here. We don't know why this is not happening and why atoms are stable. Only using classical laws we cannot explain such things. Not only this, there are so many things. For example, the radiation emitted by a black body. How do you explain that? Can't be explained using classical knowledge of physics. We need something more. So something more we need. The other example is photoelectric effect. Photoelectric effect is also a phenomenon which was very difficult to explain by the physicist before 1900, before Einstein came into this. That was also very difficult to understand. So that's why the classical physics, or in other words Newtonian physics, is not sufficient when we are dealing with the subatomic particles or the particles which are very microscopic in nature. So we need some more theories. So those theories were included. People started discovering those theories, giving those theories from the beginning of 21st century, and it has been evolving till date. So in higher classes, though this topic is given as the last topic in class 12, it is actually the beginning of a new age physics called quantum physics. So anyway, we will be studying all those things in higher classes. We will be studying that. But right now, for our course, we require only these concepts. Photoelectric effect we will study, then matter waves, what are they, then atomic and nuclear physics. So this topic, at least some 4 to 5 questions can be expected for NEET and IIT examinations. Every year, at least 4 to 5 questions will appear from these topics, from all these topics. So we'll learn one by one in detail now. First of all, we'll learn what is photoelectric effect. Yes, what is photoelectric effect? Now we know that, as I said, electrons are orbiting around the nucleus inside atom. There are many number of orbits, and electrons in the valence shell are there. They are very loosely bound to the nucleus. Now if I want to take out some electrons from the outermost shell of an atom, what do I have to do? I have to supply some energy to the electron, because each electron is having certain energy when it is orbiting around the nucleus. So if you supply minimum amount of energy to the electron in the valence shell, you can take that electron out of the atom. So that energy can be supplied in different forms. It can be a heat energy. If you supply heat energy to the electron, it gains that energy and can liberate out of the atom. So that process we call it as thermionic emission. Thermionic emission. Then we have another method called secondary emission, where you hit an electron with a highly accelerating particle, and that particle's energy will be transferred to the electron and electron will come out of the atom. That is called secondary emission. Then field emission is also there. What is field emission? Apply some powerful fields, electric fields. If you use powerful electric fields, you can take electrons out of the atom. These are the different ways how you can take the electrons out of an atom or of a material. This is another method, photoelectric. The name itself suggests photo, meaning light. So now here in this case, we are supplying energy to the electron in the form of light. When light falls on a surface, suppose this is a metal surface, and we know electrons are resting on the surface. If light is illuminated on the surface, the valence electron will take energy from the light, because light is a form of energy. So that energy gets transferred to the electron and it will be liberated out. So this effect is called as photoelectric effect. The ejection of electrons, the emission of electrons from a metal surface, when the metal is illuminated with light, is called photoelectric effect. It can be any light. Since incident light, we can say it is incident light. You can use visible light, you can use UV light, IR light, all the different kinds of light in the electromagnetic spectrum depending on the material that you are using. Each material will respond to a particular light. So based on that, the electrons will come out of the surface. Okay. So this is not the end. This is what people have observed. But some interesting things have happened. Surprisingly, what happened was, I'll show an experimental setup for the photoelectric effect. You just have an emitter or cathode, and we have an anode or collector, we can say it collector. You have a circuit, give a power supply, then put this in a vacuum chamber. Put these cathodes and anodes in a vacuum chamber. This is a vacuum chamber. This is an emitter and this is a collector. Now, since this is a cathode, I'll be illuminating it with light. Then we know that electrons will come out. Once the electrons come out of the cathode, they will be attracted towards anode, because we are giving some power supply here, a positive voltage, a voltage V. We are giving this. So electrons will reach the anode and it will form a circuit when light is fallen on the cathode. If you want to measure the current, you can have an ammeter in series, then you can measure I. But strange things have happened in this experimental setup. Photoelectric effect, we understood, this is just the emission of electrons when light is illuminated on a metal surface. That's it. But surprisingly, what physicists have observed was, using this experimental setup, they started using different kinds of light for the same metal surface. And then they varied the intensity of the light also. When I say, when you are using different kinds of light, I mean there is a change in wavelength and frequency of the electromagnetic spectrum. There is a change in the wavelength and frequency. It can be any different light. Then intensity can also be varied. So they performed the experiment by varying the intensity as well as by changing different lights, by using different frequencies of light. What they observed was, for a particular metal, for a given metal, electrons will come out only when the frequency of light is a certain value, is having a certain value. Let's say that certain value, that minimum value is F0. When the frequency of the light is certain minimum value, F0, electrons started coming out of the surface. And this certain minimum frequency for that particular metal is called as threshold frequency. threshold frequency F0. Now if you increase the frequency of light, let's say use some other frequency f which is greater than F0, no worries, electrons are still coming out of the metal surface. But if you use the frequency of a light of frequency f which is less than the threshold frequency, then they observed that no electron is ejecting out of the metal surface. This was surprising to them. When the frequency is less than the threshold frequency, when the frequency of light that you are using is less than the minimum frequency, which is called as threshold frequency, no electrons will eject out of the metal surface. This is one of the surprising thing. How much ever you increase the intensity, they did this, they increased the intensity to a large extent using the same frequency light, but still no electron was found to come out of the metal surface, even though you increase the intensity of the light to a large extent. Classically, what we think, what we assume, when you are increasing the intensity of light, you are indirectly increasing the energy of light. The energy of light gets increased when you increase the intensity, because energy is proportional to intensity of light. But strangely, when the frequency is less than F0, how much ever the intensity is, how much ever you increase the intensity, there will be no ejection of electrons from the metal surface. Then once F is greater than F0, means the light that you are using is more than threshold frequency, then electrons are coming out. They just come out of the surface. Now if you increase the intensity, once frequency is more than F0, threshold frequency, now you increase the intensity, then they observe that more and more number of electrons are coming out of the metal surface. As you increase the intensity, the number of electrons coming out of the surface will also increase. So number of electrons coming out is proportional to the intensity. This was one of the observations. So number of electrons coming out is proportional to the intensity of light. Intensity of light used. Once the electrons reach anode, they form a complete circuit and current will pass through the circuit and we can measure the current. So if you increase the intensity, indirectly we can see a large amount of current in the circuit using this ammeter. More intensity implies more photocurrent. So both intensity of light and photoelectrons ejected are linearly proportional. Intensity of light is proportional to photocurrent. So the photocurrent is linearly proportional to the intensity of light. This was observed. So these were the experimental results they have observed. Now classically what we think, classical theory predicts, classical physics predicts that if you increase the intensity, then energy should increase. Once the energy is increased, electrons should come out. Because for every metal, there is a minimum amount of energy that is required to make an electron come out of the surface. Right? Take any metal, any atom. Minimum amount of energy has to be given for the electron to just come out of the surface. Once you give that minimum energy, then the electrons are free from the surface and it can go out. That minimum amount of energy that is required to take an electron from the atom, from inside an atom to outside, to the surface of the metal, is called work function. Work function, and it is denoted by phi. This is the minimum amount of energy that is required to take an electron out of the metal surface. Once you are supplying this minimum energy, then electrons are free. They just come out of the surface and they are free to go in any direction. Once if you give energy more than this, what happens? More than this, if you are giving more energy, according to the law of conservation of energy, energy has to be conserved. So the remaining energy will be taken by the electron as its kinetic energy. If the energy is more than this work function, the remaining amount of energy will be taken as kinetic energy of the electron. We will see that. So this is a work function phi. Now, scientists before 1900, the physicists, they could not explain these phenomena. First thing is the kinetic energy of the electrons that are coming out of the metal are not depending on the intensity of light. They are not depending on the intensity of light. In fact, they are actually depending on the frequency of light. I said they observed that when the frequency is more than this threshold frequency, only then the electrons are coming out of the metal surface. If you reduce the frequency below that, no electrons will come out. And once the electrons come out, they get some kinetic energy, and that kinetic energy is proportional to the frequency of light given, not the intensity of light given. But intensity, as you increase the intensity, the number of electrons coming out of the metal surface will increase. That's why we see this graph. The current is linearly proportional to the intensity of light. So these were not properly understood by the physicists before 1900 because they were using the classical theory of light, classical wave theory of light. What it suggests, the intensity is proportional to energy of the radiation. Since if you increase the intensity, then energy has to be increased. But even though you increase the intensity, the electrons are not coming out. This was surprising to them. Even if you have least intense light, let's say you have least intense light and frequency is more than threshold frequency. Once the frequency of light is more than threshold frequency and you use the minimum intense light, the intensity is very less, even then they observe the electrons coming out of the surface. Once the frequency is more than threshold frequency, the intensity, even if it is lesser, electrons come out. And the process is very instantaneous. This photoelectric effect is an instantaneous phenomenon, meaning when light falls on the surface, immediately electrons come out. If the light is having the frequency which is more than the threshold frequency of that particular metal. And this threshold frequency will vary from metal to metal. Each metal will be having its own threshold frequency and its own work function depending on the material. So these were the difficulties to explain using classical physics. So there was a need of introducing something new, some new theory to explain this phenomena. So what Einstein did in order to explain all this, because people before that they were struggling to understand this concept clearly, more clearly. Once Einstein arrived in this picture, what he did was, he suggested a new theory. He assumed that light, which is an electromagnetic radiation, the electromagnetic radiation is quantized in small particles, which are called as photons. So he suggested that light actually is a combination of photons. It consists of photons. The electromagnetic radiation is a electromagnetic radiation contains quantized particles called photons, and he proposed that each photon will have an energy E, which is equals to hf, where f is the frequency of light, and h is the Planck's constant. He drew an inspiration from the Planck's theory, Planck's law, used Planck's constant in this. Each photon will have an energy which is equals to h into f, where f is the frequency of light. In some cases you can represent it as nu also. In some books you can find frequency is represented as this symbol, nu. So it is your comfort, whichever symbol you can use. Then what he suggested, once the frequency is a threshold frequency, that is sufficient, that energy is sufficient to make the electron come out of the surface. So if I say that frequency is f naught or nu naught, then energy of that particular light will be E equals to h nu naught. And if this energy is equals to the work function phi. What is work function? It is the minimum energy required to make an electron come out of the metal surface. If this energy is equals to phi, then electron just comes out of the surface. Therefore, h nu naught is phi, or h f naught is phi. What if you use an energy, a light energy, which is having more compared to this minimum energy? Suppose if I use E equals to h nu, where nu is greater than nu naught, what happens? As I said, the remaining energy will be, it is converted as a kinetic energy of the electron which has ejected out of the metal surface. So therefore I can give an equation E that equals to h nu, where nu is greater than threshold frequency, is equals to the work function plus the kinetic energy of the electron emitted. So h nu is phi plus Ke. This is the famous equation given by Einstein, which is called as photoelectric equation. Photoelectric equation. This phi is the minimum energy required for the electron to come out of the surface, and once that electron comes out of the surface, the remaining energy is taken by it and it is used as kinetic energy. Means the electron gains some kinetic energy once it comes out of the surface. So the total energy is conserved here. Now what we observe from this? Now as I show the experimental setup, you have a cathode here, you have a power supply here, you have an anode here, and it is covered in a vacuum chamber. This is cathode, this is anode. You have a voltage V. Then the electrons, they come out once you illuminate light on it, so on the surface of the metal. Then once the electron come out, the energy possessed by the electron is just kinetic energy, which is equals to half mv square. Now this kinetic energy is the energy possessed by the electron, and this is the maximum kinetic energy, meaning there are number of electrons coming out of the surface. All electrons may not have the same kinetic energy. The kinetic energy that I am representing here is the electron which is having the maximum kinetic energy. Only then this conservation of energy will be obeyed. So this Ke can be written as Ke max. So maximum kinetic energy possessed by an electron. Some other electrons will not have the same energy because there may be the losses in the energy when the electrons come out of the surface. So that losses, unless we know what are the losses, unless we quantify what are the losses, we cannot directly use this equation. So we take this kinetic energy is the energy possessed by the electron, and that energy is the maximum energy. That energy is the maximum energy, and all the electrons will have the energy less than this kinetic energy. So I can write it as phi plus half mv, phi plus half mv max square, where kinetic energy is given by half mv square and v is the maximum kinetic energy. So v is the velocity possessed by the electron, maximum energy, maximum velocity possessed by an electron. Therefore E is h nu, which is phi plus Ke max, that is phi plus half mv max square. So this is the photoelectric equation given by the Einstein. We will continue from here in the next lecture.